All right, it is 2, so let's get started for today. And we're going to pick up from the Friday lecture and continue our talk about enzymes. And hang in there, everybody. Just 2 more weeks of lectures left, and then test 4 in the finals. We're in the home stretch territory here. So enzymes, when we talk about biological enzymes, there's usually only 6 different types of reactions that they're going to do. And so we have our classes based on their reaction types. So here in our first example problem, we're just kind of remembering our basic chemistry and trying to determine, okay, what type of reaction goes with, on the right, what reaction am I showing? It's basically what I'm trying to say there. So let's go through this one by one and figure this out. And before we do that, I guess let's take a look at our different classifications. So first we have oxidoreductases. These are redox reactions, right? So you're going to be moving electrons, and oxidoreductase, you really know you're using these if you see something like NAD or FAD or NADPH pop up. These are usually going to be keys that we're doing the redox reactions. A transferase is just transferring a functional group from one molecule to another. Hydrolase, water cutting, right? Hydrolysis reaction. So usually water is going in, right? So a lot of the times you'll see something like this. Water goes in and you cut a bond. Lyase is when you remove something to form a double bond. Isomerase is when you're just moving a group on the same molecule. And ligases is when you are forming a bond using ATP. Most of the time, whenever you see the word ligase, that's going to be connecting nucleotides. So DNA, RNA. So if we look here in A, what we're doing is we're switching the CH3 position with the hydrogen position, right? So if we were going to look at this, and we had to pick one of the 6, this would be an example of isomerase. Because we're doing an isomerization reaction. We're just moving how things are bonded in the same reaction, right? And this isn't a transferase. This is a common question I get, because we're not like transferring in molecules here. So that's A. So B, let's see what we're doing here. We have C double bond O plus an acid. And we're going to form carbon dioxide. This is mostly a lyase reaction. Because we are removing a big group here. And a lot of the times for a lyase, you're going to form a double bond within the molecule that's being removed. But here, we're actually forming a double bond with our carbon and oxygen to make our C double bond O. So that can be an example of a lyase. C, we have our friend NADH. So whenever you see NADH, that's going to be oxidoreductase, like 90% of the time at least, probably even higher. But here we're doing a redox reaction. So NAD, FAD, NADP, you can be sure those are oxidoreductases. In D, here we have amino acid here, and ATP plus ammonia. And what's happening here is that we're removing the oxygen and we're adding this NH4 to where that oxygen was, but doing that uses ATP. So this would be a ligase. And this is a weird version of this in that we're not doing with nucleotides. This could also be possibly a transferase in that we're transferring a functional group, NH4, onto a molecule. Right? So either one of those would probably be fine in that situation. And the only reason I'm bringing that up, because even though it says ligases are bond formation with ATP hydrolysis, like I have here, you usually see ligases like with nucleotides, bringing those together. So I just want to make sure that like possibly could also be called a transferase, even though by definition it's a ligase. So I guess I'm just bringing that up. So if you ever come across enzymes and you want to refer back to this table, there could be some variation there. But yeah, any questions about the types of reactions that enzymes normally do and what they would look like? All right. So now the next thing we're going to focus on is just looking at mechanisms of some enzymes. And the reason we're doing this is so we just get comfortable with the idea of looking at mechanisms again. I know you cover these in organic, but now we're going to just look at common enzyme mechanisms. And the good thing about enzymes is that a lot of these mechanisms, they're going to be applicable to many enzymes, right? Enzymes just use the same type of chemistry over and over and over again. So here we're looking at a keto-enol tautomerization. We're taking our keto here on the left and making an enol group. And our transition state here is we're halfway forming a double bond between the CH2 and breaking this double bond between the carbonyl group here. Now, normally, this type of reaction is incredibly slow, but we can speed it up either through an acid or a base reaction. And so that's what we're looking at here. We're looking at just a general acid and base reaction. So what an acid catalyst is that you will give a hydrogen away. And what a base catalyst is, you'll take a hydrogen. So one is giving, so acid is giving, taking is a base. And a lot of the times when we look at enzymes, you will have both acid and base reactions happen at the same time. That's why I have concerted acid-base reaction catalysts. So that's what we're actually going to look at the next slide, I believe, where acid and base is happening at the same time. And for acid and base reactions, only certain amino acids can take part of that. Because as we learned about with pKa's, right? So let's just take a jog back to memory lane. So pKa is pH, where you're 50% protonated and unprotonated. And we learned that only certain amino acids have pKa. So only certain amino acids can lose or gain a proton. And only those amino acids can participate in acid-base reactions. So let's just take a look at this reaction. So here we have the acid reaction, where HA is going to represent our enzyme. And the way that we speed this up is that we are trying to stabilize the transition state. That's how our catalysts work. You are trying to lower the energy of the transition state. Here, we're lowering it by presenting this hydrogen to our oxygen, which will help to break its double bonds because the electrons will try to go to here. And when those electrons are trying to reach for that hydrogen, you will naturally want to form a double bond because this carbon would only have 3 bonds otherwise. And carbons don't want to have 3 bonds, so you're going to form a double bond here. And the way to do that is to lose that hydrogen. So we lose the red hydrogen, and now we have our enol. And then our enzyme, which is very important. This is showing regeneration. Enzymes always have to go back to their starting position, right? Enzymes work multiple times. It would be a really waste of energy if an enzyme did a reaction once and then died, because making proteins isn't cheap. It takes ATP and it takes amino acids. So you want your enzymes to work a lot before they die. And so after every single reaction, we have to regenerate our enzyme back to its starting position, which is what we're doing here, where we're getting a proton back to our enzyme. In our base reaction, we have the same philosophy in that we are trying to stabilize the transition state, but we're just doing it in a different way. Here, we are trying to take a hydrogen from carbon. When that happens, this carbon, the CH2, will want to form a double bond with the center carbon so that it can have 4 bonds, while this center carbon doesn't want to have 5 bonds. So it's going to take its double bond and give it to oxygen because oxygen has no problem being negative. Then, if we have an acidic proton floating around, that oxygen will take that proton now, and it has 2 bonds, so it's happy. And now we have our enol again. And again, we need to regenerate our enzyme here because now our enzyme, our base, has a proton attached to it. So to complete this mechanism, we would just have to remove that proton. So there is just like some general examples of like an acid and base reaction. Any questions before we move into an actual specific example with a real enzyme? Right. So the mechanism we're going to look at is RNase A, and this is concerted acid-base catalysis, in that we're doing both an acid and a base reaction. And this enzyme is in your small intestines, and its whole job is to chop up any RNA that you eat into small fragments. And to do this, the 2 amino acids that are very important for this mechanism to work are His12 and His119. And in case you're unaware, the 12 and 119 just means the position in the primary sequence. So H12 is the 12th amino acid, 119 is the 119th amino acid. Now, when you look at acid-base mechanisms, I gave a whole list of amino acids that are really good for this on the last slide. His is like a superstar, right? His has a pKa of roughly 6, and the cytoplasm has a pH of roughly 7.2. So it is very easy for histidine to exist both in the protonated form and the unprotonated form. So since they exist in both those forms naturally in the cytoplasm, they're often the amino acid used for acid-base reactions. So let's take a look at our mechanism here. And the key player to begin with is our 2' hydroxyl. Remember, this is RNA. If this was DNA, the 2' would just be a hydrogen. So this enzyme does not work on DNA. It only works on RNA. And so if we look at this mechanism, His12 is our base, and His19 is our acid to begin with. So His12 is taking the hydrogen from the alcohol group on the 2' position. When it does that, oxygen will have no hydrogen, it will be negatively charged, and so it will want to attack this phosphate molecule, or atom rather. And so it will do that. And when it does that, phosphate will have too many bonds. So this hydrogen on His 119 is perfectly situated to bond to the oxygen on the 5' carbon. So remember, for sugars, it goes 1, 2, 3, 4, 5 for ribose. So this is 5'. And so this oxygen takes that hydrogen. And you have effectively broke this phosphate bond now. It is broken. And because this phosphate bond is broken, there's nothing holding this part of the RNA there anymore. So that part of the RNA is free to leave. However, we do have a problem here, and that is we have this cyclic nucleotide where we have our phosphate bound to our ribose base on both the 3' position and the 2' position. And also, His12 is protonated, His19 is unprotonated. And like I said, we need to do regeneration. So that's what we're doing here, by the way. Regeneration. It's supposed to be an ER. In that we need His12 to go back to the base form and His19 to go back to the acid form. And to do that, a common strategy after you do like the first step or the first series of steps is just to do the complete opposite. So step 2 is the opposite of step 1. In that His12 now is acting like an acid, and His19 is acting like a base. So remember that His12 took in hydrogen from the 2' hydroxyl, and so it's going to give that back to our phosphate, or sorry, to the 2' hydroxyl. So it took that hydrogen and it gives it right back. And when you do that, you break the phosphate bond to the 2'. However, phosphate would not have the correct number of bonds to it. And so to fix that, we have water come in. Water is often in enzyme mechanisms because you're in the cytoplasm for the most part, and water's everywhere. So water will come in and it will attack this phosphorus, while at the same time, His 119 will take a hydrogen from that water. And an OH will form on the phosphorus as shown here. And now that nucleotide is free to leave because it's no longer cyclic. And if you look, we are back to our starting position. Now we can just reverse this whole thing, bring in another piece of RNA, do the same thing again, and we can keep doing that and doing that and doing that and chopping up our RNA into smaller and smaller fragments. So that is the RNA ACE mechanism, and it's our example of a concerted acid-base mechanism. Any questions about anything presented here or anything up to this point? Right. So here's a question. I'll give you, um, 30 seconds to a minute to think about. Based on what we talked about, how are acid and base mechanisms helping to speed up reactions? Here I have an example of our general acid and base, but for our ketone enol tautomerization, but for acid and base reactions in general, or any reaction really, what is the trick to speeding them up? Stabilize the transition step. That is correct. You want to lower the energy or stabilize the transition state, right? So an acid catalyst does that by donating a proton, while a base catalyst does that from extracting a proton, right? And if we go back to our previous slide, right, the intermediate step for this reaction is where like you have a partial bond forming between this oxygen and yeah, so you have the partial bond here. You have the partial bond of this breaking as well. And you also have the partial bond of this breaking. And naturally, that's hard to do. It does happen in RNA, but that's just a hard process to make happen. So to speed this up, we are having a base here to remove a hydrogen to make this bond break easier. And we have a hydrogen acting as an acid to make this bond break easier, right? So we are helping to stabilize that transition state, to lower the energy of the transition state with acid and base catalysts or any catalyst. One does it by giving a proton, one does it by taking away a proton. So very good. Right, and so here are some questions that are good review questions. I already kind of answered these, so let me just review that real quick. So in the RNA ACE, histidine acts as acid and base. Why is his good? Because of the pKa being around 6, which just means it's very good to either gain a proton or lose a proton. And why can't RNA ACE cut DNA? Because at the 2' position, which is right here, there's only a hydrogen, right? And if histidine is right here and it wants to take that hydrogen, well, that's very hard to do because that hydrogen is not acidic at all. So it won't move. Versus RNA, so that's DNA. Here we are taking a hydrogen from an oxygen that is much more acidic than a carbon hydrogen. So any questions about those ideas? All right, sorry for that delay. I had to go yell at the dogs who were barking at UPS trucks. All right. Question 4. So here I'm going to give you a couple minutes to do that again, just so we're clear on catalyst and reaction coordinate diagram. So draw reaction coordinate diagram for the catalyzed reaction and uncatalyzed reaction of RNase. And in case you don't remember what that means, reaction coordinate diagram has energy on the Y, and it has reaction progress on the X. So tell me, based on that mechanism, how does energy change with reaction progress, where this state would be like, well, actually, like when you have nothing bound, actually, sorry, keep going. When you have the RNA bound but haven't done any chemistry yet, that's like position 0. Then when you have it both broken off, that's like 100% complete. So tell me how the energy could possibly change using reaction coordinate diagrams for the RNase mechanism. I'll give you like a minute or two to think about that, and I'll come back and with the answer. If you have questions, let me know. All right, so hopefully you made some progress on that. Oops, I did not mean to make that line. Let's take a look at what these look like again. So there's just a couple of fundamental things to look at. So I'm going to draw the uncatalyzed. So uncatalyzed will be in black. So we're going to start with the reactants. So reactants. And then once you get to the transition state, you have a big barrier, right? Because that takes a lot of energy. So this is transition state. Then at the very end, at the end of the reaction, you're going to have your products. And depending on if the reaction's endothermic or exothermic, the energy of the products will either be below or above your reactants. So exothermic products below, below reactants, That means you release energy. While an endothermic reaction, with products above reactants. To do that reaction, you have to absorb energy from your surroundings. By below and above, I just mean where I draw them relative to reactants. So that's my uncatalyzed reaction. Let's go dark red for catalyzed. And the important thing here is that the energy of the reactants don't change, right? The reactant here is just RNA. This catalyst isn't doing anything to RNA, before the reaction, so RNA is RNA. What it does do is lower the activation barrier of our transition state, makes that easier to get to. But the product's energy is the same because our product is just 2 strands of RNA now that have been cut. And our enzyme's not doing anything to these 2 strands. So that's the inner reaction coordinate diagram for our RNA ACE. The only thing that's different is this gap. And if you remember, this is called delta delta G double dagger, the difference in the difference of G double dagger, while the difference between the reactants in the uncatalyzed reaction, we call that delta G double dagger. And the higher this hill is, the slower it goes. So a catalyst, all it does is it lowers the energy barrier of the transition state, making this reaction faster. All right, any questions about reaction coordinate diagrams and how to make one from a mechanism? All right, with that, we move on. Next type of reaction we're going to look at is covalent catalysis. And what covalent catalysis is, like you might think, is that you are forming a covalent bond. And here, we're going to look at the formation of acetone from acetoacetate. So just a little background about this reaction, right? Acetoacetate is what's called a ketone body. And this comes from fat. And it's what your body uses when you are fasting, because your brain can only get energy from glucose in ketone bodies. And so if you don't have glucose around, you're going to make ketone bodies. But what can happen naturally inside the body is that this acetoacetate can lose a carbon dioxide, gain a proton, and create acetone. Now, this is normally slow, but it does happen. And acetone is the same stuff in nail polish remover, and it has a very sweet smell to it. And so if you are diabetic and you're untreated for it, one of the symptoms that a doctor might look for is, does your breath smell sweet? Because if you are breathing out a lot of acetone, which is responsible for sweet smelling breath, that means you had a lot of acetoacetate, which means that your body doesn't recognize you having glucose. So that was just fun little background on the reaction that I'm showing there. Let's see how we can speed up this reaction by using the catalyst. So our catalyst here is going to be in red. And we're going to form what's called a shift base. This molecule here is an example of a shift base where you have your positively charged nitrogen attached to your carbonyl group. The R group here is just the rest of the enzyme, right? So that's just enzyme. So our first step here is forming our shift base by kicking off our hydroxyl group. And when we do that, we'll have a positively charged nitrogen, and we're going to try and not make that positive by taking electrons from this double bond. So we're going to take those electrons, and when we do that, this carbon will need 4 bonds again, so it's going to take electrons from our carbon dioxide. Carbon dioxide will fly away. And so you can see how we have stabilized our intermediate or our transition state here. We've just kind of replaced this oxygen and said, we're going to put a nitrogen there, right? And our nitrogen is going to kick off that oxygen, and this is going to be our new transition state. While after that, we have to remove the enzyme again because we have to replenish the enzyme. So we're going to do that by an acid. So an acid's going to come in and it's going to protonate our carbon here at the end. So instead of CH2, it's going to be CH3. And like I said, when we're looking at the RNA ACE mechanism, you just, to regenerate your enzyme, you just do the reverse reaction. So here we're doing the reverse reaction where at the very beginning, our enzyme came in, kicked off the OH, formed our shift base. Well, to replenish this enzyme, OH is going to come in, kick off our enzyme. Now you have acetone, and the enzyme is the same as when it started. So that is a common theme whenever you're looking at an enzyme mechanism. It'll do one series of reaction and then do the exact reverse series of reactions to replenish itself. So that is our example of a covalent catalyst, because we are forming a covalent bond to our substrate there. So any questions about that idea or this mechanism? Right. So here's a question. Why must the covalent bond formed between the enzyme and the substrate in covalent catalysis be transient? And by transient, I mean, why isn't it permanent? Why can't we just bond this enzyme to our acetoacetate here and just call it a day? We're done. No need to continue. We kicked off CO2. We are in our transition state. We're good. Enzyme needs to be reformed at the end. Yes. Do not forget that. It's rare. It does happen, but it's rare to find an enzyme that works once and kills itself. Always need to regenerate. Right, so we've looked at acid-base catalysts. We've looked at covalent catalysts. Now let's look at metallocatalysts or metalloenzymes. And when looking at enzymes in general, metal ions play a role in a lot of different enzymes. As shown on that slide, a third of all enzymes have a metal ion bound to them. So make sure you eat your metals every single day. Take a bite out of that zinc. Good for you. And the way that metal ions help are shown there. So one of the big things they do is they help to orient negative group properly. So since metals are positively charged, negative groups, negatively charged groups, will want to interact with these metals. So one smart way to speed up catalysis is to position them in your enzyme in such a way that when your substrate binds, it's going to be in a favorable position for your mechanism to work. So that's point one. Point two is that metals are really good at redox reactions, especially like iron. Iron can go from +2 to +3 super easily. And so if you need to do a redox reaction, you can use metals as a temporary storer and giver of electrons. They have no problems doing that. And three, shielding. This is especially important in mechanisms that use ATP, right? So if I draw ATP, now phosphate, 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 so there's ATP. I think that's, what's that negative? These, I think that's -1, -1, -2. You have phosphates that are incredibly negative, right? And a lot of the times, like when we look at enzymes, that phosphate doesn't spontaneously just fall off. You know, I'm sure you saw ATP to ADP in many mechanisms through biology, because that's our energy storage. That doesn't just happen. Like that ATP is stable. That phosphate's not going to just pop off by itself. So to help mediate that, you often have magnesium that help shield these negative charges, help lower the overall negative charge, which often allows cutting. Another way shielding really helps is when you're connecting DNA molecules together, right? Because and this goes back to phosphate as well. So at the 3' position, oops, that's not oxygen. You have phosphate. -2 charge. And when we are connecting it to a new nucleotide, we have the 5' carbon. And on top, attached to that is OH. And we're trying to bring these two things together. OH itself, the oxygen, is partially negatively charged. And so if we want to bring them together, usually magnesium sits between the two so that we can bring the negative charges closer and closer and closer together without them repelling each other, because you have a favorable magnesium right in the center. So that's another way metal ion to work in enzymes. So just to recap: orientation, redox reactions, shielding, electrical charge are the other three main points. You can also see them in acid-base reactions. Those of you who took Gen Chem 2 here, this is actually something we talk about very briefly. But metals make water acidic because they help pull off protons, which is actually a big problem if you do something like brew beer, because acidic water is not good for that. But this works in enzymes, metalloenzymes. If you're trying to do an acid catalyst, well, just throw a metal in there and it's easier to make acids, because that metal is helping to remove that hydrogen. So questions about our metalloenzymes here? Right. And I think, yeah, this will be our last slide. So in general, when thinking about why do enzymes speed up reactions, there's four main points. One, enzymes bring substrates together. For anything to react, they have to be close to each other, right? Well, enzymes can grab these things from the cytoplasm and physically put them together. But overall, that's only a 5 times speed up. Something that's even more important is that when they bind substrates, they're going to point them in such a way that they will want to react. So naturally, even if two things collide, if they don't collide in the right orientation, chemistry won't happen. A reaction won't happen. However, an enzyme not only grabs them out of the cytoplasm, but puts them in this correct orientation, which is 100 times speed up. So we just take point 1 and 2, you're speeding up a reaction by 500 times already. Point 3 is that, like we saw in the metals, we can help stabilize any charge groups at their transition state based on amino acids or metal ions that are around. So one of the big problems with transition states is that you might have like negatively charged carbons, positively charged carbons, positively charged oxygen, crazy stuff like that, that doesn't want to happen naturally. Well, you can just bring amino acid into the binding pocket and help to interact with that transition state. So that also speeds it up. But the biggest way that an enzyme speeds up a reaction is by stopping translational and rotational movement, right? And atoms, they are constantly moving and rotating. Like single bonds will rotate and they'll also stretch like a spring. So you have rotation and stretching going on at the same time. And what an enzyme can do is it can really stop all this translation and rotational movement by holding it still. And this speeds it up by like 10 million times. So in general, an enzyme speeds up reaction. And an overall arching theme that I've been talking about today is that they speed up reactions by lowering transition state energies or stabilizing the transition state. And they do that by grabbing the substrates, orienting them in such a way so they interact, neutralizing any charges, and making sure that the atoms don't rotate or they aren't vibrating or moving around as much. And when they do that, there is an energy penalty for this, right? And what I have an entropic penalty, because you're taking a molecule that has a lot of freedom of movement and saying, no, you only have one movement now. You're bringing order into the universe. The universe doesn't like that. So it costs energy to do that. And we get that energy when we bind the substrate. So the substrate and the enzyme usually have a pretty good fit. They have favorable interactions, like we talked about, I believe that was on Friday. So you have these favorable interactions, which allow to pay for this entropic penalty. So that's how we're paying this energy penalty, is through binding of the enzyme to the substrate. I think that is a good place to stop. We just have a couple more slides, so we'll look on that on Wednesday. But any questions about anything we have covered up to this point? All right, if not, thanks for stopping by. Thanks for watching YouTube. I will put homework up for this lecture so we can get some practice. Otherwise, hope you have a good rest of your day and hope to see you on Wednesday. Take care.